All right, so welcome everyone. I know a few people. A few people are still getting a pizza, but I think we'll go ahead and get started. Just a reminder, please sign in. There's a sign-in sheet just to prove that we have people here eating the pizza. I'll bring it back with me, so if anyone didn't sign in, just go over to me or do it before you leave, please. I think we'll just go ahead and get started. So today's speaker is Peter Song, and he's a professor in biostatistics.
Thank you, Marcia, for the invitation. And as I'm getting older and older, so I get more opportunities to speak outside of the boundary of biostatistics and statistics community. I really appreciate this opportunity to have this invitation and talking to people, working quite expensive with the biostatistician, but now really working on the methodology. So, I mean, we have shared responsibility on how we're going to analyze data and deal with complex data and design good studies and so on and so forth. But I don't think I have many opportunities to really talk directly with the people in computational biology and health informatics. I think we should have more interactions because we share a lot of common responsibilities and interests. So today I'd like to talk something simple. I know that I only have 15 minutes, so that I want to minimize mathematical formulas, the arguments, and just want to present the framework or technology that has been derived from this framework to talk about how we can have different ways to overcome data sharing barriers. So this is research funded by both my R1 and NSF methodology grant. So to begin my talk, I'd like to really introduce my lab at SPH. We sort of pursue statistical method and technologies that can help people to advance medical and public health research. A lot of the projects we work at in my lab are strongly, very closely motivated by biomedical research projects. I work a lot with people in the nephrology and also environmental health sciences. And so we have several R1 grants funded by NIH, NIDBK, NIEHS to pursue those methodology development and how we can do better for data processing and modeling and data analysis. Yeah. So if you're interested, you can visit my lab webpage. So this whole research of interest in sort of overcoming data sharing barrier begin with the panel discussion on October 26, 2016. There was a meeting workshop, precisely speaking, kind of very small panel discussion organized by, I think, 14 NIH institutes. They really say the importance of data sharing, and this has been one of the top priorities in NIH, as NIH and other federal funding agencies have invested so much money to generate data, and by funding many different studies, and a lot of data have been collected in the research studies. Then they always want to think about how we can use the data to complete the transition of data into knowledge. That was a very small panel discussion. El Hill and I were invited from University of Michigan to participate in this panel. And at that time, I knew a little bit about data sharing, but not primary in this field. And I learned a very strong sense and urgency at that panel discussion. NIH and other funding agencies like DARPA and NSF want to push this very hard, the boundary of data sharing, so that they can speed up this research discovery and save cost in general. So that after that panel discussion, that I feel that as a statistician, what I can do better to facilitate the process of this data sharing strategy, research, and other effective method that can really overcome this barriers. So that's the beginning of my research interest in this field. Okay. So of course the idea of data integration or data, combine data from different studies is very simple. People want to create bigger data with richer information so that they can do better research, right? So if you go to Google, search the keyword data sharing, this number is just huge, right? So there are a lot of interest, not only in the scientific communities, but also in industry, right? So they want make good use of existing data, in many ways that they can build up a relevant database to address some of the commercial needs or scientific hypotheses and so on. So there's a tremendous interest outside, not only in university, but also outside the university campus to do data sharing. So in talking about the scientific community, that we know data sharing is essential for better scientific research. So essentially, a lot of bioinformatics study where people want do this sort of data integration for a very simple purpose to increase sample size, because if you want to find rare 100 subject or 2,000 subject will not be sufficient. You have to do some data integration in order to increase sample size so that have better power to detect some signals that otherwise cannot be detected by a single study, right? So this is a very simple way of or idea of the motivation to increase sample size. And so another thing is that you want the data to be more representative to the general population by combining different data sources together. For example, I work on asthma study, where one study focused on only kids from elementary school, another study focused on kids from middle school. But if you want to have a more general conclusion of your research findings, that you like to combine the data together to cover a broader range of the general population, for some kind of intervention that you want to deliver. Okay. So combined data has a scientific goal where you want combined data to cover broader range of population so that your conclusion could be more generalizable. Of course, that you want to save research cost by avoiding collecting similar data that being collected in other studies. This is one of the primary interests from NIH and other funding agencies. They say, we already found this study collecting this omics data. Why we need to find the similar study, collect the similar omics data? Can such data collected from other study be used by this study? Somebody is conducting, and so they keep asking the question why we need to invest a lot of money to collect the similar data. Okay, I mean there's a general interest from funding agencies for the purpose of saving costs. Okay, and also data collection is really a time-consuming process. If you have this experience, you know that you have the recruitment, and even the IRB takes so much time. Then you start this the recruitment and all data pre-processing, handling missing data, data quality, QC procedure. It takes so much time to finally reach the analyzable data set that you can start to find something meaningful. So this is really time-consuming process if you really start with something from scratch, right? So sometimes you really want to say, hey, can I use some data that's being, cleaned and pre-processed and so on and so forth, that I can save a lot of time, so that I can speed up my research. So there are a lot of interest in others. I think you all have this kind of experience that how important that if you can, have somebody who can help you to clean data, they collect data and clean data and so on. So there are a lot of interest in scientific community to have data sharing going on. But on the other hand, that the data sharing barriers are so excessive and high in general. Due to many reasons. I work for a University of Michigan and Shanghai Jiaotong University collaborative project, where we're trying to looking at how air pollution would affect the post kidney transplantation graphic survival. So this is a joint project between University of Michigan and Shanghai Jiaotong University. That university has 7 affiliated hospitals. So 2 years ago, we went down there and talking to the PIs who are involved in the Shanghai side of this project. And it's a very interesting story. This 5 out of the 7 hospitals have their data managed by one data management company. So physically, the hospital data are all stored physically in one data storage facility, but they never share that data, even though the data are physically stored in the same computer like disk. But the 5 hospitals never share the data. So we're saying, hey, we need the patient data who received the patients who received transplant, and so we can look at air pollution, association air pollution, and post-transplantation graphic survival. And it was a very interesting discussion about how we can come up with some strategy to share data. One person from one hospital asked, who is going to be the first author of the publication that we're going to have? So, what? I never saw this question, but there they asked this question: who is going to be a senior author, the first author of a paper that you're going to use our data to do the analysis? I say, I cannot promise you to be the first author. Sorry about that, but so there are a lot of reasons beyond this data privacy and confidentiality. People a lot of time are talking about the patient's data privacy, confidentiality. But there are a lot of incentives. People don't speak out. They create a lot of barriers due to many reasons as well. And ownership of data is not clear. And one time we discussed about this. So I have no authority to share data with you. So when you talk about who has the authority, nobody knows, right? So it's not very clear defined. So who can push the green button to let the data be shared with us? So, and I already mentioned the incentive for data sharing. So when you have some of the findings, who will be having this sort of credential of those research results, and more peculiar reasons, and something like, you know this is not an easy issue to overcome. So the current platforms of data sharing is really built up on the centralized database. When you think about this whole sort of mandate, data sharing priority by NIH, other funding agencies, they always want to build up a centralized database. Right? So, okay, you have data, John has the data, Joe has the data. So let's just bring them together, right? So build a centralized database that contains the identified raw data from data donors. This is actually the current thinking of data sharing. Okay? And so in order to avoid the data privacy and confidentiality, a lot of the time, people release their data to the centralized database. They just transform data. For example, the one of the very sort of commonly used strategy is to lower down the resolution of data. I have a continuous variable, but I don't want to share my continuous original measurement. I just want to discretize this. Okay, you still get the variable, but you don't get originally measured variable. You'll get a discretized version of that, right? So another thing is the people do add a little bit of noise. Okay, a noise jittering a strategy where they say, okay, I don't want you see the original variable or measurements. I add a little bit of noise on that. Okay, so the variables are masked by some noise, and so this is very active research field in computer science, something called a differential privacy. So they want to impose the noise in a proper way so that a particular type of statistical analysis, like linear regression, is not going to be affected. Okay, so I can inject noise to the variables, but at the end of the day, if you receive the sort of noise-affected data, contaminated data, you still get the same result as if you use the original data. But this noise injection strategy is analysis-specific. If you do linear regression model, you have to inject the data in such a special way so that you can keep the same sort of findings as if you run the original data. If I run logistic regression, I run Cox regression, you have to do something different. So this is really analysis dependent noise injection. This is not universally sort of the same sort of strategy. You have to study all different strategies, depends on what analysis you want to do. So that's the you know, there are some strategies, but all the strategies are built upon this concept of centralized data sharing. So for example, I say this is a very bad idea of lower down this sort of resolution. So I just did a simple simulation where I have a linear regression model. Very simple linear regression model. So X1 could be your ohmic marker, could be copy number variation or methylation or metabolite, whatever. You have a confounder, let's say H. Okay. So you have some health outcome. So you run a linear regression so that you know, these two predictors or covariates are correlated, and then you're interested in the effect size, or you make some analysis association between this biomarker and your health outcome. Okay, so then you suppose you have sample size 200, then you repeat this analysis 5,000 times. Okay, so one analysis here is that you discretize this confounding factor because H is somewhat like a sort of identifiable variable. That's something associated with the privacy and confidentiality. So you don't want to release the original measurement of age of the subject in data sharing process, that you want to discretize it. Suppose you do this dichotomization, you put it into two categories, 3 categories, 4 categories. So here's the result. If you don't do anything, use the original data, so no problem, linear regression model is right. So you get your right estimation. And if you do the model 2, which is the case where you dichotomize your confounding into 2 categories, you convert your continuous H variable into a binary H young old. Okay? So you get the estimate that this. If you do this 3 categories, 4 categories, so you can see that. If you do this transformation of your variables to a lower resolution, okay, in the data sharing, you bring a lot of strange things in the data analysis. As a result, you have overestimated effect size association. Okay, this is a serious issue. Okay, it's not just like you fulfill this obligation of data sharing. In the same time, you protect the data privacy. But at the same time, you create a misleading statistical analysis. Okay, this is very serious. Okay. So the take-home message one is don't arbitrarily change data for the sake of the identification if you don't know possible consequences. People do this all the time. There's no understanding of the consequence of statistical analysis. Because I cannot give you the original measurement. I just discretize it. I still gave it, right? But you can see that for this very simple linear regression model, you just don't get the right solution. Okay. So that's a very serious issue that you have to think about. So now here's come to our sort of solution. How we're going to do this, okay? So I call this collaborative inference. It consists of several sort of elements. First, this is a distributed statistical inference in the sense that this statistical inference is conducted under a collaborative agreement of data analysis plan or common analysis protocol. So you have 200 hospitals or 20 hospitals or 2 hospitals. You plan to share data to do certain data analysis. Let's sit down together, not talking about data sharing. Let's work out a data analysis protocol. What kind of analysis we plan to do? Okay. So how we're going to prepare our data, how we're going to choose our model for the analysis, and then how we're going to interpret the result. So you have all the elements in the protocol, okay, set it up, and all agree with it, okay? So that's the first step you do. After you get this protocol designed, then you say, okay, I'm a statistician. I'm not going to receive all the raw data from this 20 hospital. What I need is give me just summary statistics. Okay, give me mean or standard deviation or some information matrix. I don't need your raw data. Okay, we agree with each other that we're going to run linear regression model. Just give me the estimate and the standard error of your regression coefficient. I'm sitting here in the University of Michigan, and I don't want to get your raw data. The raw data are still stored in your local disk. Okay, I only need the summary statistics. Send those to me. Then I will ask for the summary statistic. I don't need to do access to raw data at individual sites. Okay, that's easy. I don't need to do raw data. And so this analysis is not based on centralized database. I'm not going to pull all the local data sets into a centralized database. Data are still just stored in the local places. I only need you to send me summary statistics according to analysis protocol. Okay, and so the analysis will be operated separately and remotely in a distributed fashion. Okay, so the resulting analysis, I'm sitting here as my job here is you give me summary statistics I request. I'm trying to find an optimal way to combine information so that the resulting analysis is not going to have any loss of statistical power. Okay, so suppose you have the centralized data, you do the analysis, okay? You have a power, okay? You generate p-value, something like you want your statistical power there. Now I request summary statistic. I will retain the same statistical power as the centralized analysis. Good deal. See, I don't need to access the raw data, but I can still do this analysis that has the same power as if you do the centralized. Okay? So that's something I want to advertise. So it's something, can you do this? So this architecture, so you first work on the protocol. You have, like in this case, 8 different research sites where you have a consorting of 8 participating sites. Each site holds their own data and operating data locally. So what I want here is to request some summary statistics, mean and standard deviation, something like that. Then I can combine them to generate result here. And the result would have the same this analysis will have the same statistical power as if you combine data together to run the centralized analysis. Okay, so that's the new platform I want to do. So my first question here is why we need a common analysis protocol, because this is very, very critical, right? I mean, so the first question here is why is a common analysis protocol needed? Okay, here is a simple simulation. So using the same setup, where now X1, the biomarker is a non-marker. It has no is not the important marker. So that you like to, I mean, of course, when you do this omics biomarker analysis, you always run linear regression and test the sort of the association. Suppose X1 is a non-marker, so it's not associated with the Y. So I still have the same setting. Now I'm just saying that, so if you decide to, like for the model 1, where you say that I'm not going to include confounding factor in analysis, okay, so X2 is my confounding factor. So if I only do just marginal analysis of X1 without using confounding, that's the t-statistic distribution. This is the t-distribution when you use the full model. Okay? And this orange one is the one that you decide to run marginal. Okay, so you can decide to run marginal without adding confounding, but all places should agree with that. Okay, that's what I'm saying. Now, if you say, oh, different places have their different way of dealing with your X2, then your t-distribution is running around. There's no way that you can, oops, sorry. They grab the statistical power together. The t-tested statistic, you have dichotomization, you have one place that doesn't use this confounding factor analysis. I mean, then this distribution is wandering all different places. You don't really get the right distribution that can really help you summarize information to take advantage of data sharing, data aggregation. Your distribution is everywhere, right? So then, at the end, your finding will be problematic. Okay. So what I'm saying that you have to agree what analysis you want to do in advance, so that this distribution can become narrower and narrower, get more and more power. Because if you increase the sample size with different treatment of X2, you cannot really shrink the precision of this distribution, get more power, because the distribution is wandering in all different places, right? You have become a multi-model distribution if you combine it. So you don't really take advantage of sample size increase, okay? So you have to agree this. So that's basically the problem about meta-analysis nowadays. People just take a parameter interest out of the published paper, not talking about the course of publication, just talking about just using the, a popular result. You don't know what X2 has been handled. They have different structures handled. If you only just pull the information from X1 to conduct meta-analysis, maybe you end up with something like this, right? So in my personal view, meta-analysis has been largely abused in the medical publication, even more seriously abused than p-value. Okay, so there are a lot of discussion about p-value nowadays, even within this community. Say we should not use p-value, we should use p-value, we should interpret p-value in different ways, so on and so forth. There are a lot of controversial arguments, discussion about the meaning and the domain or boundaries that p-value should be used. Okay. However, I think meta-analysis is an even more serious issue. There are about, I just did a Google search, there are about over 100,000 publications using meta method in the medical journals. But if you different studies using different way of dealing with confounding factor, you will end up with something like this. It's not going to really give you something meaningful, or even some findings you have will not really interpretable. So you have to have a common protocol in place. So the second question here is this more critical question from a statistical point of view. What summary statistic we should pass around? Okay. So I said that I don't need summary statistic. I don't need raw data. But the question here is which summary statistic actually carry the critical information, okay, and passing should be shared in this sort of collective inference. So I gave you a very simple example to illustrate this is the way that is doable, is the feasibility example. They consider very simple setting of two independent normal samples with a common mean parameter. That's the mean population mean, okay? Average height or something, a blood pressure, if you want estimate, and some heterogeneous variance. You have two populations. You sample M subjects from one study, and you sample N subjects from the second study, like second hospital. So then you believe that they have, you are interested in the population average attribute, which is the mean of that, right? So you want estimate B. So what you like to do here is, of course, you want to use this two data set together to estimate the mean parameter B. Okay, so very simple idea. So now you do centralized method. So okay, so hospital 1 and hospital 2 agree to share data. They put their Excel sheet together so that you can have two data combined to create a centralized database. Then the mean can be easily calculated, right? So you just add the first data together and second data measurements together and divide by total sample size. Very simple. And this can be decomposed in such a way that, you know, B1 is the sample mean of the first data set, and B2 is the sample mean of the second data set. Okay. So, but anyway, the first line is the way that you will calculate. You know, when you have the centralized database, you just add them together, divide by total sample size. That's very straightforward. But what I'm saying here is that the sample mean, this statistic, is distributable in the sense that I don't need the raw data. If I'm interested in the population average mean estimate, if you only pass me the mean of the first data set, I don't need the raw data. The other one pass me the mean of the second data. I can still calculate the mean exactly as if you have done this using the centralized data, right? So the reason you can do this decomposition or this distributed calculation is mean is a linear function of your data. So if you have a linear operator of your data, a linear operation of data, you can always split them into chunks or segments and process them separately in a distributed fashion, right? So this is great. It tells you that if you want to calculate sample mean, you don't need really data from all raw data from different places. You don't need the local mean sample mean. But the question here is this strategy works for logistic regression? Because in the logistic regression, you have a nonlinear regression model. Your estimator, your regression coefficient does not even have closed form expression. How do you do this decomposition? If you run Cox regression, your estimator has to be solved by Newton-Raphson iterative algorithm. You don't have closed form expression of your solution. Unlike the mean, you have closed form expression. You can decompose it using this, very elementary mathematics skill. But if you have Cox regression, you have a random effects model. You have logistic regression. How do you do this? Your solution cannot be even written out, can only be solved numerically using iterative algorithm. So one side that it's great that you see that this is distributable. On the other side that you would ask the question, okay, would the sample mean enough for me is to solve this problem? Or is this the way that optimal? Because I said that collaborative inference will keep the same power as you do the centralized. This is my centralized solution, which can be distributable if you do this way. But my question here is that is this way of combination give you optimal solution? So you can keep the the power. So that's the question we need to solve, right? So what is the optimal way to combine these two pieces of sample mean? So this back to the Fisher's fiducial paradigm. 1935, Fisher published a very interesting paper. He called this fiducial, but this never be taught in any courses in statistics, or I don't, probably some of you have never heard of this. Okay, so I think it's a very good way of thinking. Of course, Fisher is father of statistics. He did a lot of thinking at the very early time of statistics. His thinking is not from mathematical, technical way. His thinking was very philosophical and think how we are going to best use information, how we are going to best extract information from data. Okay, fiducial is one way of that thinking. Okay, he said that, well, we first need to generate knowledge of the new parameter from one data set, because I have two data sets coming from two hospitals. He said, okay, how am I going to first, what if I generate the knowledge of mean parameter from one data set, then obtain an updated or posterior estimator B using the second data set. So he defined this sort of sequential strategy. I use first data set to generate knowledge, and then I incorporate this knowledge generated from first data into the second data set in an optimal way. So the question here is, what kind of knowledge we should generate from the first data set? Okay. So according to Brandon Efron, he called this a holy grail. Okay. Can you find that holy grail, okay, from data you have? So this solution was presented many, many years later by Efron in 1993. He pointed out in a study of his bootstrap. Okay, so when you think about bootstrap essentially is a method of information aggregation. You generate the many kind of, you have this regenerative model. You stimulate from this regenerative model some kind of bootstrap samples. Then your question here is how you're going to optimally combine the multiple samples together to get your estimate and inference. So Efron has to face the question of data integration in the bootstrap. So he looked at that kind of issue and published a paper in 1993 saying, hey, this holy grail is something called a confidence distribution. Is a distribution estimate, this is mathematical, that is needed, used to construct confidence level, any confidence level. So what's the knowledge about this parameter from my data? If I'm able to construct confidence level of the parameter of interest at any confidence level, then I should say that I have a full understanding about this parameter. So my summary information is sufficient for me to make inference. So he called confidence interval, and this is contain all knowledge about the inference. So what is this guy, the holy grail, that in the linear situation? Efron said that is this one, is the distribution of your parameter with the sample mean as the mean parameter and the variance of over the sample size. Okay, so this is a distribution. Now people say, oh, this is prior, but this is different prior, right? This is a distribution derived from your data. You start with nothing, okay, and you only observe this data set. Then you say, I'm going to learn my parameter from the first data set, and what's the best knowledge, or the maximum knowledge you can extract from the first data? Efron says is this one, this distribution. This is the distribution you use to construct confidence interval of the parameter, mean parameter, based on first data. Okay, so but technically you can treat this as your prior. Then you have your second data set, right? So you say, oh, I have my first data that create a fake prior, this holy grail. Then you can use Bayes formula to calculate a base estimator, okay, then I just use the base formula. Okay, so given that fig prior from first data, that's the result. Okay, so you can see that fiducial estimator is also a linear combination of these two sample means. So B1 is the sample mean from first data set, B2 is the sample mean from second data set, but they use different weighting. This weighting is very familiar to you. This is the meta estimator weighting, the famous meta estimator. The weighting makes sense. The weighting makes sense in the sense that, so what is MS1 minus 2? This is actually the variance of sample mean. The receptacle of the sample mean. So what do you say if B1 has the data, first data has very low quality, meaning that it has very large variance, a lot of noise, you should downweight that sample mean in the contribution of the combination. Very natural, right? So if I have a lot of noise in this data set, I should not use this data set as much. So the way to control the contribution of that poor data set is through this reciprocal, the sample variance of that sample mean. Okay, very natural way. So this is really a distributable thing because you only need to use two sample means to overcome this. But the question here is this optimal? Okay, apparently that this one has different coefficients in the linear combination. Well, this combination is optimal because I said that I want to keep this same statistical power. Okay, this comes to the work of Gauss and Markov. We call in statistics Gauss-Markov theory. Okay, this theory guarantees that the way fiducial constructed combined estimate is optimal. Okay, this is math, but I like to walk over because very intuitive. Okay, beautiful math is supposed to be very intuitive, very, very data driven. Okay, so I have two sample means. I want to combine create a combined estimator. So I have one coefficient C1C2 defined by my centralized method I just showed you. And also I have C1C2 determined by my fiducial, Fisher's fiducial argument. So I have many, many other coefficients I can use. But the question here is, which pair of C1C2 that will give me smallest variance, namely the highest precision for this combined estimate? This is a very natural thing. I have two pieces of information. I want to combine this together. So which way I'm going to combine so that I can have most precise estimate? So you basically want to find optimal C1C2 so that the combined estimate has the smallest variance, highest precision. You need to have this constraint C1C2 plus 1 because you want the combined estimate to be unbiased estimator. Well, you don't want to create a bias after you do the combination. So this constraint guarantees that the combined estimator is a unbiased estimator. You don't have bias, right? So that's what it was. So if you do the simple, Lagrange sort of optimization, the solution is this. What is this? This is exactly same as fiducial estimate. So what I'm saying here is that you have these three pieces of master work together. Fisher's thinking of fiducial sequentially. How do you aggregate information sequentially? Then you have Efron's work on how you're going to generate knowledge. And then you have Gauss-Markov to tell you this is optimal. Okay, this must be a good combination with all the great minds in statistics and mathematical community. I really enjoy this. I say, oh my God, that's something we have to do some further generalization. Okay, so I want to sort of recap a little bit. Fisher's fiducial estimator of population mean is distributable in Hadoop, Spark, blockchain platform. Basically, you don't need access to raw data. It's most precise one among all the linearly combined estimator. I just approved. And the centralized sample mean is optimal only on two variances parameters the same. In other words, the centralized estimator is not optimal even is obtained under the full access to all raw data. Okay? So how do you believe that the data collected from two hospitals would have the same variance? No heterogeneity. It's not possible, right? So I think there are a lot of heterogeneity exists in actual data. You always have the case that you have heterogeneity, so that the centralized method, as we did, may not be the optimal. Okay. So what I'm saying here is that this collaborative inference is win-win situation. First, it doesn't require to access the raw data. You just store your data as you like. I only request summary statistics. You give me. This is a very reasonable request. Just give me. I don't need your all data, right? Secondly, I argue that this way I combine, I give you optimal solution. Okay, that I'm not losing anything. Okay, don't think about I'm losing anything. There's nothing. Okay. So now it comes to this only one slide. I'm talking about tools and technology echoing the theme of this seminar. So after understanding those very basic thinking from those masters, then we say how we're going to generalize this. Okay, so that's what we did in my lab, generalizing the fiducial paradigm to important statistical model, linear model. Generalized linear model, including like logistic regression, log linear regression, and log linear negative binomial. I know that a lot of people working on this in bioinformatics. Yeah. So how do you do Cox regression? How do you do longitudinal generalized estimating equation and random effects model, quantile regression, structured equation model for mediation analysis? So I just show you how this is possible, feasible to do mean parameter. But in my lab work out all the solutions for all these important models. This is the tools and technology I'm talking about today. I don't have time to go over all the details. Okay, but you understand that what I try to achieve and what I have achieved, that if you come to this data sharing sort of issue and like to overcome the barriers, you just tell them, oh, I have a colleague at UM who can, just request summary statistics, no raw data. Okay, just calm down. You don't need to give me raw data. Give me summary statistics. I can produce the same result, even better power than what centralized method can do. So this is take-home message 2. The collaborative inference has no loss of statistical power or even gains higher power when data are heterogeneous in comparison to centralized analysis with no need of sharing raw data. Okay, so that's what we have been working on in my lab. So I just want to show you a quick simulation longitudinal study. Okay, it's very, just want to show you that we have this toolbox available for longitudinal study. So you have a consortium of 200 hospitals. Each hospital has 500 patients collected, and you can have a centralized analysis, basically combine the data from 200 hospitals together, and then you can run. After you have the centralized database, you can always run, the standard analysis like linear mixed effect model or generalized estimating equation using the R package G or SAS proc, mixed, right? So here is the analysis is, and then you have the collaborative inference I just talked about. We call this raw method because we're motivated from C.R. Rao's idea of how this can be done. So we call raw estimator. So here we do not require any raw data in the analysis. We only request point estimation and information matrix, like feature information as standard output from your, site, individual site analysis. Then you can get the result. Then you look at relative efficiency. So this smaller, this is the one that you use centralized, and if you use our method, that you have a small standard error as expected, because our method is more efficient, because you reach the lowest, the smallest variance. Okay, so you can prove that mathematically, but numerically it also shows in this very simple longitudinal study, our method can produce more precise the estimator with higher precision without accessing raw data. Okay. So here's my concluding remark. So collaborative inference has not need to build a centralized database. So raw data can be stored in a distributed fashion in local steady size. In this way, variable will now be changed to lower resolution or max with artificial noise. So you don't need to change your stuff. You know, you don't need to share your variables with me. You don't need to dichotomize your age variable. You don't need to add noise on some of the variables. Just give me summary statistics, right? And this is very comfortable to a lot of the PIs who will be probably agree immediately to, you know, share some of the analysis results under the common study protocol. So as I said, that we only require summary statistic, and then those no loss of statistical power, and sometimes can have even higher power than centralized analysis. And so this is a new data sharing platform associated with technology, you know, for many important statistical models that we work in the past few years. Thank you very much for your attention. Questions, comments, suggestions?
Very important topic, and it's a great presentation. Thank you. So I guess, you know, it's great that you know, you're finding this sort of, you know, way, but to analyze. I think it's sort of a huge step forward that you only need summary statistics, obviously, right? Because it opens a lot of doors, I imagine, to a lot of data sets and things like that. So but I mean, the framework that you described, right? So it is sort of applicable to a number of different analysis methods, right? So you're doing different types of regression, and so on and so forth. So how, from, I guess, you know, from statistical standpoint, how amenable do you think it is to, you know, what other types of analysis?
Like network analysis, clustering, and classification.
Like that. Is that possible too, you think?
There are a lot of things we can explore. We haven't done anything about classification or clustering yet. But if you do model-based clustering, it's basically the logistic regression to some extent, right? So logistic regression is fine. But you will have mixture models, like you have this mixture model. I don't know, like we haven't really looked at it. But in the field that I work on, do a lot of association analysis and causal inference that we use a lot of the regression, conditional regression model and something like that. So we focus on a lot on the regression. But machine learning is another field. I mean, the computer scientists propose this data differential privacy sort of thing, adding some noise into data. I don't like that. Because the noise is additional randomness in addition to sampling randomness. So a lot of time people just take this injected noise or uncertainty as there's no uncertainty. Because if I do different people may have different ways to add noise into variable. So when people do this analysis, they have to count this uncertainty and noise injection or jittering strategy, in addition to sampling error. So they just come up with some of this sort of differential privacy idea and prove this concept in very simple setting. But you know, for us, we run a lot of more complex situations, right? So so I really like something that would be analyzed with no noise injection, right? So just keep the original measurements, find different ways. But yes, we should explore more other setting of like machine learning. That's not been done yet.
Any other?
So I'm from the library, and I oversee our research data services program.
Right.
And so I first of all want to say I really appreciate the thought and attention that you've given to data sharing and how we could make it happen in your particular field. So I'll ask this question with really little knowledge of your field. How much work does it take you to do to get the data, the summary statistics that you generated, in addition to what you would ordinarily do? So if I understand your method correctly, the different data sites would host the data sets, but then when you contact them, they would deliver the data that you needed to them.
Right.
Would it take them, would they do that work ahead of time, anticipating that you would request, or would they have to do that at the time of request, and therefore have to figure out when to make time for it?
Very great question. I think you're talking about implementation. So there are multiple ways you can implement this, right? So you can set up a centralized sort of calculator or analyzer. People can all put their data there. With the password protected.
Sure.
They run this. They save their result in a common folder.
I see.
So I don't need your data. Your data after it's run, then it will out. So I can set up the computer. That's called confederate system architecture. Another is that a lot of the places, they have their own biostatistician, because in the medical studies, right, you have consortium that consists of many participant sides. They have their own statistician, and then we can all agree about some analysis. They can run analysis, pass these things to me. So there could be a automatic way or some kind of human involved way that all can sort of give this implementation. And so that's great things that how this can be implemented in different way.
Yeah, I really appreciate the detail that you paid to the what, what has to happen to make this work.
Yeah.
I guess I'm interested in sort of the how, like how would it be implemented.
Right. The implementation certainly is very, so I need more NIH money to complete the implementation process. I can set up something that people can run and there the infrastructure, people can access and run this and that use our algorithm to combine together. So this way they can get the result right and fast. Yeah.
All right, let's thank our speaker one last time.
Thank you.